Hello. So this is going to be moving on to chapter 6. So alkyl halides, and specifically we're going to be talking about the substitution reactions. There's actually two different types of mechanisms. We're going to call them SN1 and SN2. And so what a lot of organic chemistry is based upon is the polar covalent nature of the bonds. And so if you have something negatively charged, it's going to be attracted to that partial positive charge. And so for here, right, so if you have an alkyl halide, the halide is going to be a lot more electronegative than the carbon, and so you're going to have this polar covalent bond feature where the carbon is positively charged and the halide is partial negative. And so any nucleophile that has a negative charge is going to be able to come in here and it's going to be attracted to that. So when we're talking about primary, secondary, and tertiary, so we're really talking about the carbon that group is attached to. How many other carbons are attached to that? So for here, the carbon halide bond is here. There's one other carbon attached, so it's primary. Here, it's secondary because there's two. Here, there's three, so it's tertiary. It's always the carbon that the group is attached to. The only exception would be the nitrogens, the amines. There we talk about how many carbons are attached to the nitrogens, but that's the exception. Otherwise, we're talking about the carbon that the group is attached to. Halides can also be on sp2 carbons, directly onto a double bond. So it doesn't matter if it's just a regular alkene or a benzene here, right? So it's still on that double bond. So So it can occur. Actually, they're going to have slightly, if there's an sp3 or sp2, I suppose actually sp, I guess technically too, they're going to have slightly different properties, and we'll talk about that in this chapter. So for these substitution reactions, okay, we're going to talk about the nucleophile and electrophile. So nucleophile, electrophile, leaving group, I should say. The nucleophile, right? It's nuclear loving. It's positive loving. So it is negatively charged. It's going to have some negative character to it. It either be a partial negative or a full negative, but it also has to have a lone pair, because that's what's going to use to make the new carbon bond. So the new bond to the carbon. The leaving group does exactly what we say. So it leaves, and usually what's going to happen is it's going to take electrons with it, because the carbon can't have more than 5 bonds. It's going to need to break a bond, and usually what's going to happen is it's going to push those two electrons in that bond onto the leaving group to have it go away. So the electrophile is that's the part that has the positive charge, in that it also has the leaving group. So the one with the leaving group, it's got that partial partial positive of the polar covalent bond of the carbon halide. So for here, right, the OH is going to be our nucleophile. It is going to attack that, right, because there's a partial positive, partial negative, right? So this has a negative charge, so it's going to be the nucleophile, right? So CH3I, right? So it is there is lone pairs here, right, on this leaving group. But that's okay. This is going to be the nucleophile, because this has the negative charge. So these electrons are going to get attracted to the polar covalent bond here, right? So it's going to get attracted here. This carbon already has 4 bonds to it, right? Can't have a 5th one, and so it's going to push these electrons onto leaving group to make your methanol, and that's how all of these work. Okay, so the nucleophile, the mechanism, it's just this. It's the nucleophile attacking the positive side of this polar covalent bond. So if it's a carbon, the carbon can't have its 4th bond, so it's got to push the electrons away from the 5th bond or whatever it is, and usually is going to be going on to that leaving group, breaking the bond. So you're going to substitute whatever your nucleophile is for your leaving group here. It's usually a halide, typically a bromide or a chloride. So the nucleophile itself is going to have negative characters. So it's either going to have a full negative charge, or it could have a partial negative. So that's fine. But it is definitely going to attack the positive side of the polar covalent bond, right? Negatives going to get attracted to positives. Okay, the leaving group, it basically allows the carbon to get rid of the 2 electrons and avoid having 5 bonds. Okay? So the nucleophile comes in and attacks here, pushes that away, right? And you've made your new bond. Now the methyl here, right? We didn't do anything with that bond there, stuff like that, and so it becomes. So it just comes along for the ride. I've had a lot of students over the years come in and just swap, just put an oxygen here. That's not right. We didn't do anything to that bond, so it's maintained. So the positive charge here, right? The sodium here, all it's doing, it's a spectator ion. It's just there. It's following the negative charge. So one of the things you need for a leaving group, right? One, it needs to be stable on its own as a negative charge. So it either needs to be very very electronegative. It needs to be a really weak base. So we know chloride is really stable, right? That's why we have salt, stuff like that. But things that can also provide resonant structures. So acetate's a pretty good leaving group because you can generate a resonant structure to help stabilize that negative charge. So it needs to be a pretty weak base. Those make the best leaving groups. Okay, the SN2 mechanism, guys. So this is the first type of attack. Oh, I didn't talk about this. Sorry. I just talked about this one here, where the nucleophile comes in and actively pushes this away. So as this bond is formed, this bond is breaking, and so you end up getting the swap. Okay? The other way that you could do it is the leaving group just leaves on its own to generate the carbocation here. It's typically carbocation, right? And then the nucleophile can come in and attack. Okay, you could say, well, why couldn't this negative charge come back and attack? Well, I'm sure it does, but the product would just be this, would just be original starting material, so you wouldn't notice it. It's only when the nucleophile itself comes in and attacks that you actually make the new product. So there's 2 different types of mechanisms. This is the SN2 mechanism. This is the SN1 mechanism. We'll talk about those specifically. So the SN2, you get this direct attack. Okay, so the nucleophile directly attacks the partial positive here to actively kick away the leaving group here. These 2 electrons form a 4th set of lone pair on the chloride here, on your leaving group, something like that. But as this bond forms, this bond is breaking, right, and pushing this away. And notice how the hydrogens were originally pointed this way, and over here they're pointed that way, and that actually is going to become very important in a minute. If you look at if you visualize what's going on, as the reaction's moving along, right? If you're actually able to plot what's going on with the energy, so your reactants are some energy level, some arbitrary energy level. Okay, it's going to cost you energy to get everything aligned and to start breaking this bond here between the carbon and the leaving group. It's going to cost you energy, something like that. But after this is released, you're going to hopefully get a stronger bond in the end. Okay, and so overall, the system is at a lower energy. Remember, nature's lazy; it wants to be at its lowest energy state, and so you've actually dropped in energy. So it's good. So it's like paying paying $2 for the lottery ticket to win $10, right? You have to spend a little money to make money. So if you drop in energy from where you start to where you end, that's good. It's what's called exergonic. You can also call it spontaneous. Now you have to be careful about spontaneous, non-spontaneous, right? Because non-spontaneous is where you start at a low energy level and actually end up at a higher energy level. That's non-spontaneous. The system actually wants to be down here. Okay, so so spontaneous, non-spontaneous is just looking at these energy levels, and that's it. Look at that. So it doesn't talk about speed. So diamonds, the classic case is diamonds. They are actually a system like this. So if you have a diamond, It will eventually turn into a lump of graphite, but it's going to take 1 billion years to do it. So it is spontaneous. It will happen on its own if you just let it sit there long enough, but it's not speedy. Okay. The other thing I forgot to mention is this gap here, how much you have to put in, right? So we talked about the $2 lottery ticket to win the $10. That $2, that's what's called your activation energy. That's the initial investment the reaction has to put in order to be able to get the reaction to go overall. And it's just the amount of energy from where you start up into what's called the transition state, where it's sort of a half bond here and a half bond here. That's the energy committed by the system in order for the reaction to go. And so for here, the transition state or the activation energy would be here, would be huge, right? And in the end, it doesn't get as much, right? So here it's a $10 lottery ticket that you only get $5 out. That's not good, something like that. So this would be non-spontaneous. It would actually rather be back down here. Okay. Now the way that you make this work is to so remember, with energy and temperature, it is actually the average kinetic energy of the system, of the particles in the system. And so if you have if you were to measure, if you measure the energy of each individual particle, okay, and then the how likely it is that reaction, when two of those things collide, it's actually going to happen. It's only going to be some small percentage, okay? And this is what's called a Boltzmann distribution, okay? At low temperature, right, most of the collisions aren't going to amount to much because they're not energetic enough to break to get over the activation energy. So but all these guys have like 50 cents or $1. They can't buy that $2 lottery ticket. Okay, but if you start throwing money around, right, you start heating these up, giving everybody a little bit more energy, right? Now more of the people are going to be able to buy that lottery ticket, right? So they're going to have enough money to have enough energy to get over that barrier. So so now we've increased the temperature. So typically, if you want to speed up a reaction, you heat it up. Now you have to be concerned about the fact that you don't want your materials, if they're thermostable or thermally unstable, you don't want it to turn into like goo at the bottom of your round bottom. So you have to be careful. But in general, if you want to speed up a reaction, you heat it up. Okay. Now remember when I said, look what's going on with these hydrogens? Well, with the SN2 reaction, what's happening is you have to come in from the back side, right? So in order to be able to break this bond, you have to push it away. Okay, you have to actually push. Okay, so for that, and so in order for that, it has to come in from the back side. It has to come in 180 degrees from where that leaving group is. So as this is coming in, this is breaking because you want to get into this transition state where it's a half bond here, and then boom, it breaks. But notice what the hydrogens are doing, right? They're initially pointed that way, and then as they come in, they snap over here. Okay, when that happens, you actually invert the stereochemistry. Well, this isn't chiral center here, so it's not. But if it was, you would invert it. So you can see here, right? So with this the cyclopentane here, so if you get attack here, it's got to come in from the bottom to be able to push this away. So it's like kicking your brother or shoving your brother in the back, right? So you need to push it away. But because you're coming in from the backside, now you are down here. Stuff like that. Notice it went from up to down. So you're going from cis to trans. Stuff like that. The other way that you could do it, right, is you go from the R, right, as you attack, these groups have to slide over here, right? And in doing so, you go from an R to an S. Okay? So with that, so you invert the stereochemistry. Now, the other way that you can do the substitution reaction is what's called an SN1 mechanism. And this one, the leaving group is going to go away. You're going to, it just leaves. And you are, what you're going to be left with is a carbocation. The nucleophile, in this case it's water, is going to come in and do the substitution. Now, eventually you're going to get that H off of there because the oxygen has the plus charge. But essentially what you're doing is you're substituting the water here, which turns into an alcohol, for that Br. It's essentially the same reaction. Okay. It's called SN1 because it's a substitution, nucleophilic, and unimolecular. So in the first case, right, the SN2, the reason why we use the 2 is that the fact that in that first step, which is the slow step, the rate determining step, there's actually 2 molecules coming together and colliding. Okay, so with that, so that's why we call it SN2. For this one, the first step is going to be it's just one molecule falling apart. Okay, it has no bearing on the other molecule. The nucleophile has no control over that. Okay, so with that, and so that's why it's called SN1, because there's only one molecule involved in that first step, which is the rate determining step. So if you look at what how fast this goes, the conditions, what you want to be able to stabilize that carbocation, okay, that leaves, right? Because you're going to have a leaving group go away, yeah, so with that, and so resulting in stable carbocation, you want it to be tertiary, right? Because this carbon here, right, it's going to have 1, 2, 3 friends. So tertiary carbocation's not too shabby. But primary carbocation is really unstable, so this is very unlikely to happen through an SN1 mechanism. Secondary, it might happen, but definitely tertiary. It's going to go through this mechanism. Okay, and it all has to do with this the stability of the carbocation. The reason why this happens is the carbons themselves that are right next to it can actually assist in stabilizing it. So it's sort of like if you have to move a couch, it's easier to have 3 of your friends help you move it as opposed to 1. Okay, so with that, and so tertiary is going to be better. Secondary, primary, methyl is really unstable. The hydrogens can't really help you out here, but the carbons can. So SN1 is all about carbocation stability. So the term for this is hyperconjugation. So the other thing that you notice is that when you go through this carbocation, if you go and calculate the hybridization of that carbon, the carbocation is in fact an sp2. Okay, and it has this open p orbital here that it can accept the lone pairs from that. From the nucleophile, but when it's in this transition state here, where it's a carbocation, the molecule itself is actually flat. It only has 3 bonds, which makes it a trigonal planar orientation. Okay, so it goes flat. The consequence of that is that when the nucleophile sees this, if it attacks from the front side, it's going to push the groups this way to make this stereoisomer. If it attacks on this side, okay, it's going to push the groups this way, and so you're going to make this stereoisomer. So no matter what happens, no matter what you started with, you're going to get a receiving mixture. You get R and S out at the end. Okay, so with that, so when it goes through that carbocation information intermediate, you lose all information. Okay, about what's going on. So if you if you have an SN2 reaction, if you start off with R, your product's going to be S. If you started with S, you're going to end up with R. Okay, for SN1, it doesn't matter which one you start with, R or S, you're going to get both of them out at the same time as a product. Okay? So the kinetics of this, okay, so for an SN2, remember that everything's happening in one step, right? 2 molecules are colliding, so it's going to depend on the concentration of your leaving group, right? The electrophile and your nucleophile. Both of them are going to make a difference. Okay. So with that, so you can write this out in a rate equation, right? So the rate is some constant times the times this concentration times this concentration. Okay. So if you were to measure what's going on, you measure what's called the initial rate. So things can kind of slow down once you start up start building up product. So with that, and so you just measure the first little burst of product formation. And so when you if you were to just do like 1 and 1, so that these concentrations here, you get some rate. Okay, if you were to double this concentration, okay, you would in fact double the rate. Okay, if instead you doubled this your nucleophile here, if you compare this to this, the first 1 to 3 here, again you're going to double the rate. Okay, because they're both part of that rate equation. If you double both of them, right, it would be 2. You're going to double this times doubling of this, and so in fact you get 4 times out. So you would actually end up, it would make it 4 times as quick. So For an SN1 mechanism, right, you only deal with your electrophile here, because that first step is the leaving group leaving, so it has no bearing the concentration of your nucleophile. Okay, so for here, if you double the rate, right, if you double the concentration of your electrophile, you will double the rate. Okay, but if instead you were to double the concentration of nucleophile, it's not going to make a hill of beans of difference. Okay, if you double both of them, again, it only depends on this. So doubling everything is going to just double the rate. So with SN, so I'm not going to have you actually calculate the numbers, but you have to know how this changes, right? So if you were to triple the rate on an SN2 case, right? So with that, so 3 and 3, right? 3 times, right? The overall rate would be 9 times faster. If you were to triple the rate on an SN1 mechanism, it'd only go up by threefold. So with that, 3 times as fast, because it only depends on this. So increasing this 3 times and increasing this 3 times, the nucleophile doesn't matter. It's just the electrophile concentration. So it would only go up threefold. So the factors affecting SN1. So for SN1, SN2. So for SN2, it's really about structure and speed in some ways. So that's really about what. So because what you really want to do is, because you're directly attacking, that nucleophile is going to have to push those groups, the other 3 groups away, and so with that. And so the bigger these groups are, the harder the nucleophile is going to have to work in order to be able to do that SN2 attack. So what you really want is to have either a methyl or a primary going. All of this bulk here it's going to be too difficult for the nucleophile to attack and push that bulk out of the way. Okay, but for SN1, it's all about carbocation stability here. So for this one, you're going to have a tertiary carbocation. So for that works great. Methyl and primary, those are the carbocations from there are going to be incredibly unstable, so it's just not going to break apart very often. So with that, so the reaction is going to be really slow. Okay. So if you're going to change for an SN2, changing electrophile and nucleophile, both of those are going to affect the rate. But if you're changing the electrophile, is the only thing that's going to affect the rate. So so the factors affecting nucleophile. So with that, so in general, for a molecule, you can there's a trend of negatively charged nucleophiles are almost always going to be more reactive than the conjugate acid, so uncharged. Okay, so like that. So in the same group. So if you're looking at oxygen as nucleophiles, the stronger the base, the better the nucleophile is. So this is a much stronger base than the carboxylic acid or the carboxylate, which is a stronger base than just plain water. So for that, so it parallels basicity for the same atom going across. It's not always easy to tell with different atoms that are going to be your nucleophile, so it becomes a little more complicated. Okay, so factors of solvent type. So this is a big one. They always ask this on the MCAT and ACS final and things like that. So if you want solvent types, SN2 is going to want polar aprotic solvents. So with that, so the aprotic meaning that all of the hydrogens are bound to carbon. Okay, so for that, and so acetone, DMSO, DMF, acetonitrile, things like that. Those are your classic ones. But if you can just if you can draw the structure, if all those hydrogens are hanging off of a carbon, then it's aprotic. And the reason for this is that you can bind up the ions, right? You can bind up the nucleophile, but it's not bound very tightly. Stuff like that, and so you don't have it can when it's solvated like this, it can still easily break through and attack. Okay, with SN1, you're going to want a protic solvent. So in the molecule, it's going to have at least one hydrogen that's not bound to a carbon. Okay, so for water, it has 2, right? Ethanol would be another one. It has that OH bond. This one here is going to help stabilize this. Okay, so summary, what do you want? So for an SN1, you want a tertiary your halide in the tertiary group, you want to have usually end up being a weak nucleophile because you want to avoid the elimination reaction, which we'll talk about in the next chapter, and you want a polar product solvent. For an SN2, you want it's really almost about speed and structure. So for that is speed. So you want the leaving group to be on as small a group as possible. So primaries are great. Methyls are great. You want to have a pretty strong Lewis acid so it can get in there and make a tight bond. But this one you want polar A product solvents. Okay, and the better the leaving group for both of them, the better it's going to be. So if you just look at the halides, iodine is the weakest conjugate base, so it's going to be the best leaving group. Fluorine's a pretty decent conjugate base, so it's going to be a pretty bad leaving group. Okay, so the reason why we're talking about this is the fact that you can make all of these functional groups through this SN2 type mechanism, through the substitution mechanism, and so you can do all of this. That's why we're interested in it. Okay, and don't forget when you do this, when the SN2 reaction, remember you invert that stereochemistry, so don't forget that. Okay, so for here, so predict the product, something like that. So. Right. Okay, so this has the negative charge, so this is going to be the nucleophile. Right. Here's our polar covalent bond. Right. So here's our leaving group. Okay. So this is going to attack here. Right. Attack that carbon, and push that away to make. Oop. So oxygen. Here, there. Okay, so we've made it a bond from using this electron from this oxygen to that carbon here. So this set of electrons becomes this new carbon-oxygen bond here. So for this one, Cl plus right there. Right? So again, this is the negative charge. This is going to be our nucleophile. Right? This is our leaving group. So we're interested in this polar covalent bond here. So this is going to attack there and push that chlorine away. And so you end up with SCH3. Okay. So I guess I forgot this is Br minus, right, over here. This is the Cl minus here. But for me the important stuff is the organic component. Okay. So the SN2 does happen in biology quite a bit. So with that, and so the classic one is S-adenosylmethionine. So the way that it works is it takes ATP and you take methionine, you react it, and so your triphosphate group here is in fact just a leaving group. So that's a nice SN2 chemistry. So you make the S-adenosylmethionine here. This part here of the molecule, the red and the black part, that's just a leaving group. It's the chemical equivalent of a methyl bromide. Okay, so so your nucleophile here is if you're going to try to make choline, right? You need to put that methyl group. You get a nucleophilic attack here. These electrons go on to the sulfur, just like they would work if this were to attack a methyl bromide, right? The electrons would push onto the bromine, and you're left with S-adenosyl homocysteine and choline here. But one caveat to this, okay, in order for an SN1 or SN2 to work, they have to be on an sp3 carbon. If that halide is hanging off of a carbon that's part of a double bond, doesn't matter if it's an alkene or a benzene, it's not going to work. It's not going to go through this mechanism. Okay, there are other ways of removing those and substituting those, but it's going to be a completely different mechanism. So you cannot undergo SN1 or SN2 chemistry if the halide is hanging directly off of a double bond. Okay, so if you look at here, right? So with that, you got your, and so you say, well, which reaction worked better? So you've got your nucleophile here, your leaving group. So this is going to attack there, push this away, make this product, no problem. So you've got here, this is your nucleophile, come in here, attack, kicking off the bromide. Again, you're going to make this product, right? Either one should work well, but the problem is, right? This here, the bromine is hanging off of a carbon that's part of a double bond. It's part of an sp2 carbon. So this reaction isn't going to work. Okay, so with that, so this is the reaction. This top reaction, that's the one you would have to use if you needed to make this product. Okay, that's it. Good luck.